There are numerous specialized machines that can solve the ordinary 3x3 Rubik's Cube. However, it seems that roboticists have neglected manipulating the mirror cube, and we sought to change that. We thought this would be an interesting problem because unlike a normal Rubik's Cube, the mirror cube shapeshifts. We began by generating a virtual model of a 2x2 mirror cube. We created a script to quickly generate SDF files for our cubes with differing parameters. In this example, we have two cubes of different sizes. Here, the cubies of each cube are different sizes. And here, the layer spacing between the cubes is different. We also could set friction coefficients for the cubes. This parameterized script approach allowed us to quickly tune the realism of the cube to reduce the gap between our simulation and real life.
One of the defining challenges of the mirror cube is its off-center axis, which create non-uniform rotations. Unlike a standard cube, the mirror cube's rotation axes are misaligned with its natural geometry. As illustrated in the simulation, these unique dynamics required us to develop a system that adjusts the gripper's trajectory to ensure precision during rotations. This approach was crucial for maintaining control over the shape-shifting puzzle. To manipulate the mirror cube effectively, we anchored one QB while allowing the others to rotate freely. This setup simplified the problem and ensured consistent interaction with the robotic arm. In the simulation, fundamental rotations such as U, R, F, and their inverses were implemented as the building blocks of our solving strategy. Each rotation was standardized into 4 phases: entry, grip, rotate, and exit, ensuring transitions began and ended at the ready pose. This structured approach facilitated smooth, controlled movements and minimized the risk of misalignments during manipulation. Additionally, we simulated a virtual 2x2 Rubik's Cube to compute appropriate trajectories for various configurations. Adjustments were made to accommodate changes in the cube's shape, enabling precise planning and execution. Our experiments aimed to optimize critical parameters such as friction, spacing, and QB alignment. As we observed, these factors significantly influence the cube's mechanics and solvability. Initial tests focused on cube geometry, gradually expanding to parameters governing interactions between the EWA robot arm and the cube. We quantified performance by measuring the angular deviation of QBs between expected and observed positions. Through systemic tuning, we minimized errors, ensuring the maximum angular deviation remained below the cube's tolerance threshold, enabling subsequent rotations. This validation demonstrated the system's reliability across diverse scenarios and highlighted the potential for applying similar techniques to manipulate other dynamically changing objects.
We were able to string together sequences of moves, however we did not quite manage to scramble the cubes and execute a proper solve on a scrambled cube. With that in mind, there are future research areas we would be excited to see realized. One thing we'd like to implement in the future is capturing the state of the cube at any time with the use of computer vision. This would not only give us the initial state of the cube to solve, but would also provide feedback as to whether or not our moves were successful or not. With this state feedback, we'd also like to implement a PID controller in a leaf system to make our turns more accurate. And finally, we were especially excited at the prospect of solving a mirror cube with a dual robot arm system.